Hey everybody, welcome back to another AP Biology video. To go along with our genetics practice problems, we have another tool in our belt to help determine if we are working with something that is following the rules or not following the rules. When it comes to statistical analysis, we can use a prescribed formula in order to analyze data given to us in order to determine whether or not our results are statistically significant or if they are likely due to chance. So this is the chi-square equation. This will pop up a couple of different times from this unit to unit 6. And you will be expected on the AP exam to be able to analyze some data given to you and be able to identify whether or not you could support or reject what we call a null hypothesis. So that seems like a good place to start. When you have been in previous science classes, you may have used the more general definition of hypothesis, which is what you predict will happen as the outcome of your experimentation. How do you think your independent variable will affect your dependent variable? When we look at statistical analyses, we kind of expand on this idea a little bit. Your traditional hypothesis is going to be what we refer to as an alternative hypothesis. The idea that your independent variable in some way affects your dependent variable. But we add in a secondary hypothesis, which is the one that we can either prove or disprove in each of these cases. That is the null hypothesis. Null is essentially a word that means nothing. So that is exactly what we're describing with this hypothesis. It's saying that two variables that we look at are completely independent of each other, i.e. that there is no effect or relationship between them. Everything is 100% random. And then we have the opposite of that, which is the one that we typically think of when it comes to a hypothesis. And this is a statement that predicts the relationship between two variables, either positive or negative. So there are a number of different statistical analyses that you could use when investigating data. One of the ones that we like to highlight in AP Biology is that of the chi-square goodness of fit test. So this is a statistical analysis that we can use to determine if a distribution differs from what we would expect. So we're going to be dealing with two values primarily. We're going to be dealing with observed values, that is the data that has been collected or that we collect from a system, and the expected values, which are these theoretical ratios. So these are that 1 to 2 to 1 that we would expect with a monohybrid cross. They're the 9 to 3 to 3 to 1 that we would expect with a dihybrid cross. That is why I've mentioned at least that it's important that we remember these ratios as we go into some of these problems. It saves you a little bit of time from having to really work with the laws of probability in order to figure them out. So let's look at this equation. So chi-square, chi is a Greek letter, it looks like an X, is going to be equal to the sum of, which we represent with a Greek letter sigma, and that is the sum of our observed minus our expected values squared and then divided by our expected values. Now, one of the ways that I like to really illustrate the breakdown of this equation is by setting up tables. So let's say that we have a hypothetical experiment, that we have crossed two heterozygous pea plants are crossed, so they have a dominant and a recessive allele. And I say, well, my null hypothesis would be that there's no difference between the ratios that we're observing here and the ratios that I expect given a Punnett square or my knowledge of monohybrid crosses. And then my alternative is saying that there is something happening. There is a statistical difference between what I'm observing and what I'm expecting. So let's plug in some values. In this case, we have 83 green offspring and 17 yellow offspring. In a traditional Mendelian cross, we would expect these ratios to be a 3:1 green to yellow, that dominant phenotype to our recessive phenotype. So how do we get how many expected do we need? First thing that we want to do is to add up the values that we've observed. So here we have 100 individuals. And so I would also expect to have 100 individuals. And then I'm just going to establish my 3:1 ratio there. So I would expect 75 green for 25 yellow. That's my 3:1 ratio. From here, we have some general arithmetic. So if I follow across, we're going to take our observed, 83, and subtract our expected, 75. And we would do the same for our yellow, 17 minus 25. And so you'll see here that that gives me an 8 and a -8 for green and yellow respectively. From here, I'm going to square those values. So 8 and -8 squared will give me the same value, and that is 64. And so each of these numbers, now I do one final step. I'm going to divide each of these values by our expected. So for the green, I'm going to divide 64 by 75. And for the yellow, I'm going to take 64 and divide it by 25. And that'll give me some nice decimals there. Now, chi-square is a sum. So I am going to add up my final column here to give me my chi-square value. Even though chi-square has an exponent, we are not solving for chi, we have chi-square. So you do not need to do anything more to this value once you get it. So we're going to take this number and we're going to hang on to it for a second because there are a couple other things that we need to figure out. One of those is what we call the degrees of freedom, which are the maximum number of independent values in our data set. We have a nice little equation for that. That is, the degrees of freedom are equal to our number of categories or potential outcomes minus 1. So in our case, we have two potential outcomes. We can either have green offspring or we can have yellow offspring. So I'm going to say that my degrees of freedom are two possible outcomes minus 1. So my degrees of freedom are 1. So I'm going to be looking at the values in my 1 column for degrees of freedom. So remember our chi-square value from earlier. That is going to help us determine if we can either reject the null, so that is to say there is some statistical difference, or we fail to reject the null, which is a roundabout way of saying that no, there is no statistical difference. Everything is exactly as the null hypothesis described it. We are looking at something that is completely random. So we have two statements that we can make here, and it is dependent on whether or not our chi-square value is greater or less than our critical value. So we determine our critical value by looking at the column for our degrees of freedom. So we're going to be looking at that 1 column, and we will compare the values in that column to our chi-square value. So the chi-square value that we found earlier was 3.14. And we want to say, is it higher or lower than the critical values that are in our degrees of freedom 1 column? So here we see that we are lower for the p-value or probability value of 0.05, and we are lower than our probability values of 6.63. So since we are lower than both of these critical values, we can say we fail to reject the null. These proportions are exactly, they're not statistically different than what we would expect. So monohybrid crosses, whether we're dealing with complete dominance, incomplete dominance, codominance, these are pretty simple. But when we get into something like a dihybrid cross, we may have something a little bit more complicated. So remember, Thomas Hunt Morgan really liked to use fruit flies to demonstrate a lot of his characteristics. So let's say we have a secondary question here where we have a wild type female fruit fly. She is heterozygous for cinnabar or red eyes, cinnabar eyes, sorry, and normal wings. So we're heterozygous for traits A and B. And she is crossed with a male fruit fly who is homozygous for red eyes and vestigial wings. So these are our two recessive characteristics here. We are homozygous recessive for both characteristics. If we were to break this cross down, I've already gone ahead and done some of the probability math for us, but we would expect our offspring to have ratios that were equal across our 4 different potential outcomes. You can take time on your own to see if I've done my math right or not, or we can just go with it. And then we can compare these expected values to what we actually produce. And so let's say that instead of these quarter values for each of our potential outcomes, we saw these values. So we've got a 0.42, a 0.08, a 0.09, and a 0.41. And the way that I've found these values is I've taken the number of the offspring that have that particular trait combination, and I've divided it by the total. So sometimes they will give you the decimals or the frequency of your different traits. Sometimes they will just give you the number and you have to find the frequencies. But really our question is the same. Are these results significant? So I would do much the same as I did with my monohybrid practice problem. I would want to set up a table. Now for a table like this, I obviously now I have 4 potential outcomes, so I've had to expand it a little bit. But we would do the same as we would plug in our observed values. We would then determine our expected values based on the total number of individuals we have. So we would expect a quarter of each of those, so 575. And then we would subtract observed minus expected, 965 minus 575, 185 minus 575, 206 minus 575, 944 minus 575, and that would give us our first column's worth of values. Then I would go and square all of those obviously rather large numbers already, so we may be able to make some some inferences here. So I would take our values and I would divide them by the expected. That gives me a chi-square value of 1002.6. So from here, I do much the same as I did previously. So I would take my degrees of freedom. In this case, we have 4 potential outcomes. So my degrees of freedom are 4 minus 1 or 3. So I'm looking next to the 3 column, and I am presented with the same potential statements to make based on this data. So I'm going to look at my chi-square value, my gigantic chi-square value, and I'm going to say, am I greater than or less than the critical values in that degrees of freedom 3 column? So I am obviously larger than the 0.05. I am larger than my 0.01. And so I will say that we can reject the null. Something is happening here, and 9 times out of 10, this is how we determine that there are linked genes at work that were not inherited independently. So we're going to have some fun in class with this equation. We're going to do a few practice problems with just general probability and maybe eat some candy along the way. So I will see you guys in the next video where we will be ready to jump into Unit 6.